Welcome back to the You Can Do TV channel.
The Fantini 70 SUP-H chain saw machine demonstrates high-precision cutting performance in large-scale marble extraction. Equipped with a 6.20-meter cutting arm, the unit advances along the quarry bench with controlled linear motion, producing clean vertical and horizontal cuts in massive white marble formations. Its stabilized track system, high-torque motor, and continuous saw chain enable efficient block separation while minimizing microfractures, making it a preferred solution for dimension stone operations requiring accuracy and consistent block quality. Granite mining at an open quarry represents one of the most demanding extraction processes in the dimension stone industry. Each stage is engineered to manage the immense density of granite, control fracturing, and produce uniform blocks ready for precision sawing. Before any cutting begins, the quarry undergoes extensive preparation. Geological teams identify fracture lines, assess bedding direction, and map the bench layout to determine optimal cut paths. Access roads are reinforced for heavy machinery, water supply lines are installed for dust suppression, and the cutting platform is leveled to provide stable footing for quarry equipment. Once the site is ready, the primary cutting operation begins with a high-powered chainsaw machine. In many granite quarries, a Fantini-style unit is deployed, featuring an integrated electric control panel and a hydraulic indicator panel that monitors operational pressure. The cutting chain measures 26.37 meters in total length, allowing deep, continuous penetration into the rock mass. A dedicated reducer powers the vertical lifting and lowering motion of the blade, enabling controlled downward cuts that follow the pre-marked quarry lines. As the machine advances, the chain's hard metal segments grind through the granite, generating a smooth kerf along the bench face. Water jets operate continuously along the blade to reduce friction, cool the cutting components, and flush out abrasive stone dust. Once the cut reaches its full depth, the chainsaw is repositioned to create secondary vertical and horizontal cuts, forming a three-sided separation that defines the block to be extracted. Following the cutting phase, heavy equipment takes over. Excavators with reinforced boom arms move into position along the open kerf. Using calculated pushing force, operators apply pressure to the pre-cut section, gradually widening the separation. The goal is to exploit the natural bedding line while avoiding uncontrolled fracture. Water continues to be sprayed during the stage to reduce dust and help reveal any microcracks. Large granite fragments and wedge stones are cleared away by the excavators until the block begins to shift. With steady pressure, the block finally detaches from the quarry wall and falls onto the prepared dust bed below.
Se si strappa il filo rimane lì.
Once detached, the large block is moved to the trimming zone. Here, diamond wire saws take over for precision shaping. The diamond wire system consists of a continuous loop of steel cable embedded with industrial diamonds, tensioned between motorized pulleys. As the wire spins at high speed, it slices through granite with remarkable efficiency. Operators use this system to create square or rectangular blocks, removing irregular edges left from the chainsaw extraction. The precision of this method ensures minimal waste and maximizes the usable volume of each block. After shaping, the block is transported via wheel loaders or heavy-duty forklifts to the technical inspection area. Technicians measure dimensions, evaluate structural integrity, and classify the granite according to quality grade. Parameters such as veining pattern, grain distribution, and color consistency determine each block's intended application in the processing plant. Once approved, the block enters the production line, where multi-blade gang saws or high-speed diamond saws convert it into slabs. The block is anchored on a steel platform, and dozens of parallel diamond blades descend at controlled speed through the granite. Water continuously circulates to cool the blades and remove slurry. The result is a stack of raw slabs, each uniform in thickness and ready for surfacing treatments.
Appena me. Vai. Vai, 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 vai. Bassa. Vai, vai, vai. E? Basta, Vuoto. Vieni avanti un po'. Vuoto. Vuota, vuota. Vuota e alza. Vuota un po'. Alza, alza. Vai indietro. Vai, 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 vai. Vai, vai. Abbassa giù. Abbassa, abbassa. Abbassa, lascialo andare giù, non va da nessuna parte, vai. Abbassa, vai. Vieni.
After sawing, the slabs move to the finishing area. Automated polishing lines, equipped with progressively finer abrasive heads, refine the surface to achieve finishes ranging from honed to high gloss. Calibration machines ensure perfect thickness, while resin treatment fills natural pores and enhances structural stability. Final inspection verifies surface clarity, flatness, and color continuity before the slabs are crated for international shipment. Throughout the entire workflow, cutting, pushing, wire sawing, measurement, and slab production, granite mining relies on synchronized engineering, precise machinery, and strict safety protocols. From the first cut on the quarry face to the final polished surface, the process transforms raw geological formations into architectural materials used in buildings, monuments, and infrastructure around the world. At the Deer Isle Hostel in Down East Maine, a massive 26,000-pound block of Deer Isle granite becomes the centerpiece of a centuries-old craft. Here, buildings are raised the way they were in the 19th century, when foundations were set with locally quarried stone, structures that, even today, look nearly untouched by time. The method relies on simple but precise tools, feathers and wedges. Inserted into a series of drilled round holes, these components expand gradually as each light hammer tap increases pressure along a controlled line of fracture. This is the first major block the mason attempts to split alone, destined for a woodshop designed to echo a classic New England barn. As the wedges are driven deeper, a faint crack forms between them. With patience, the sound of the fracture progresses down through the crystalline structure. Slow tapping is essential. Microcracks form within the granite and naturally migrate toward one another when given time, helping guide an even, predictable split. Over the course of roughly an hour, the stone begins to groan, pop, and open. Water seeps from the widening fracture, revealing how close the block is to giving way. Soon the crack runs clean and square, top to bottom, until the granite finally separates into two massive halves. From this 150 cubic foot boulder, the team will eventually create 20 uniform blocks. each measuring 8 inches by 16 inches by 5 feet and weighing about 800 pounds, leaving enough stone remaining for future projects. InterContinental Shanghai Wonderland stands as one of the world's most extraordinary engineering achievements, an eco-friendly luxury hotel built not above the earth, but deep inside an abandoned quarry. Instead of rising toward the sky, the structure descends 88 meters into the massive Shenkeng pit in Shanghai's Songjiang district, transforming a scarred industrial site into a global architectural icon. Covering nearly 100,000 square meters, the quarry features near-vertical rock faces, which pushed construction teams to pioneer entirely new methods. Everything, from piling sequences to material transport and tower crane installation, required tailored solutions never before attempted on such terrain. To avoid further damaging the pit, designers chose to follow the quarry's natural contours. The hotel's main body was anchored along the pit's rim, then secured against the curved cliff wall. For Chief Engineer Li Chalfei, stabilizing that cliff was the defining challenge. Massive square concrete blocks were tied to pre-stressed anchor cables and bolts, functioning like colossal steel stitches, binding the rock together. Crews installed 99 anchor cables, each 35 meters long, along with 6 500 rock anchors driven roughly 10 meters deep, reinforcing a total surface of 760 square meters. Over 12 years, the structure slowly ascended from the quarry floor to ground level, accumulating more than 40 patents in the process. When the building finally met the horizon, it became a landmark, proof that bold imagination can turn forgotten places into enduring treasures.
Feel the precision as the production line at A2C France moves with unwavering efficiency, handling double walls and floor slabs with thorough automation. Every corner of the facility is alive with coordinated motion, yet nothing is chaotic. Each pallet begins its journey in the fully automated cleaning station, where separating agents are applied to prepare the surface. The cleaner sweeps over each pallet with consistent force, leaving a perfectly prepped surface. The system ensures that every pallet is uniformly coated, removing any residual debris and preventing concrete from sticking during the upcoming casting stages. Even pallets of slightly different dimensions are treated uniformly. The first contact with the automated cleaner almost feels like the pallet is receiving a spa treatment, perfectly prepped for its structural duties. Small particles are whisked away, leaving no trace of dust or grit. Once cleaned, pallets move to the workplace system designed for the manual positioning of supplementary parts. Operators insert additional components as required, filling in the small gaps where robot precision may not reach. Every supplementary part is positioned with a careful hand, maintaining structural integrity. This blend of human oversight and automated efficiency keeps production both flexible and consistent. The balance between robot placement and human adjustment is remarkable. Each placement is checked for alignment and stability, ensuring that reinforcement layouts will fit perfectly for the next steps. Tools for verification slide easily across the workstation, speeding up quality control. With the pallets ready, frequency-controlled cross-lifting cars transport them transversally along the production floor. The synchronized movement maintains a seamless workflow, preventing delays and keeping every station supplied at optimal timing. Each car accelerates and decelerates with calculated precision. The movement is smooth but powerful, demonstrating the force behind modern automated logistics. Sensors ensure no collisions, even in tight corners. This automated transport feels like a perfectly rehearsed ballet. Next, the preparation and placement of reinforcement takes center stage. Robotic arms take over, picking steel bars and positioning them precisely on the pallet. Robots handle even irregular bars without hesitation. These robots execute their movements with unwavering consistency, a sharp contrast to the manual adjustments made by workers in the next phase. Once the automated placement is complete, operators perform manual completion and quality control, adding final touches to ensure every bar sits exactly where it should. Every adjustment is deliberate, correcting the smallest deviations. You can almost feel the attention to detail in every hand adjustment, the human touch guaranteeing structural integrity. Workers check spacing and overlaps, confirming every joint. Concrete application follows, fully automated to maintain a consistent layer across each prepared pallet. The machine deposits concrete carefully, then simultaneously compacts it to eliminate air pockets. The concrete spreads evenly without any manual smoothing needed. The compacting motion is powerful yet controlled, like a choreographed push of energy solidifying the structure. This stage is critical. Even minor inconsistencies can compromise wall strength, so the combination of automation and precision engineering is crucial. Flow sensors monitor the concrete level constantly. The concrete spreads evenly across the pallet, flowing into corners and filling every space around the reinforcement. It fills cavities with remarkable uniformity. Once the concrete is applied, pallets are moved into the storage and retrieval system. Heated racks in the curing chamber maintain optimal temperature and humidity for the curing process, ensuring the concrete gains strength evenly. Each rack is carefully calibrated for thermal consistency. The sight of the pallets sliding effortlessly into heated racks feels almost like watching a controlled army of components settling into their disciplined positions. The automated system monitors each pallet, optimizing time spent in curing for maximum quality. A pallet overtaking station ensures that production flow remains continuous. If a pallet requires temporary holding or needs to bypass certain stages, the station provides the flexibility to reroute without interrupting the line. The station adapts to sudden changes without slowing downstream operations. It's surprising how a small adjustment in flow prevents potential bottlenecks, keeping the production rhythm perfectly balanced. This step may seem minor, but it underpins the efficiency of the entire system. Every move of the pallet is tracked digitally for precision. For double wall production, pallets are transferred to the specialized turning area. Here, the first shell of the wall is rotated precisely to create the second shell. The overhead pallet turning device allows for controlled movement, preventing misalignment or damage during rotation. The device grips securely, eliminating any wobble. The rotation feels almost alive, like the shell is being gently coaxed into a new position, ready to take on its second layer. The accuracy of this movement ensures that the two layers will integrate seamlessly, forming a robust double wall. Overhead sensors guide the turning device, ensuring exact angles. Even heavier pallets move effortlessly. Once turned, the double walls and floor slabs are transported to the loading area. A tilting station with an adjustable support beam allows operators to safely load the walls without risk of damage. Support beams adjust automatically to the slab's dimensions. The support beams are precisely positioned to hold each slab securely, accommodating variations in thickness or weight. Watching the tilting and securing process, it's almost like the walls are being guided into place by invisible hands. Safety mechanisms engage if a wall shifts unexpectedly. A mobile lifting platform assists in the handling of double walls, allowing them to be moved with minimal manual effort. The platform lifts and positions the walls, ensuring they can be loaded, stored, or prepared for shipment without stress or strain on the operators. This setup feels like muscle and intelligence packed together, every move calibrated for efficiency. Operators control the platform effortlessly with simple inputs. The smooth operation of the platform reduces the chance of human error and accelerates production pace. Even the heaviest walls feel almost weightless during handling. Finally, a shuttle car system supplies inside loader racks, feeding the line continuously and ensuring that each station has access to the pallets needed for upcoming processes. The shuttle cars stop and start seamlessly without causing delays. The system's coordination with upstream and downstream operations maximizes throughput and reduces downtime. Sensors confirm pallet presence before loading. The shuttle cars almost look tireless, as if they have endless stamina to keep the production line flowing. Their movement is synchronized perfectly with all other machinery. Every movement is timed precisely, contributing to the flawless rhythm of the plant. The system handles peak loads without hesitation. In conclusion, the high automated production at A2C France ensures efficiency, precision, and consistency at every step. The integration of robotics, manual oversight, and automated transport creates a seamless workflow. Each wall and slab meets stringent quality standards before moving to the next stage. Construction crews at the Amur gas processing plant pushed the site toward completion, with overall progress reaching 75.1%. Startup Complex 1 is commissioning, connected to the Power of Siberia Maine gas pipeline. All 4 commercial and feed pipeline tie-ins are complete. Feed gas flows into the dehydration and treatment unit at Process Line 1, while AN. Ladoga GPU-1 prepares for hot start and GPU-2 aligns for cold start. Dehydrated gas reception is set up at the ethane, NGL, and nitrogen-helium mix unit. Functional tests run across Process Line 1. The first 3 spherical tanks are ready, and water treatment commissioning has begun. Equipment coordination here is next-level efficient. NNN.
Step into the plant and see ore transforming into high-grade copper concentrate at Kokula Concentrator. It's fascinating to see how components from over 12 countries arrived in 2 485 truckloads and were integrated on-site. The concentrator, constructed in 18 months, features high-pressure grinding rolls and Jameson flotation cells, the first of their kind in the DRC. The 400-ton crane placing the mills makes you appreciate the sheer scale of this operation. Run-of-mine ore is delivered at 475 tons per hour to the crushing and screening plant, preparing the material for high-pressure grinding rolls. The grinding produces finely liberated copper sulfide, ready for the flotation process. In the rougher scavenger flotation circuit, reagents are introduced to form a slurry, then air is blown into the flotation cells, lifting copper minerals to the surface. The material passes through high-grade cleaner flotation and scavenger cleaner circuits to maximize copper recovery. After flotation, the concentrate moves to the thickener, reducing water content to 60% solids, then proceeds to filtration. Bagging handles over 500 high-grade concentrate bags per day, with half sent underground as backfill to reduce environmental impact. Tailings are carefully managed and pumped either to underground areas or to a tailings storage facility monitored according to international standards. After flotation, the concentrate moves to the thickener, reducing water content to 60% solids, then proceeds to filtration. Bagging handles over 500 high-grade concentrate bags per day, with half sent underground as backfill to reduce environmental impact. Tailings are carefully managed and pumped either to underground areas or to a tailings storage facility monitored according to international standards. Towering over the flat coastal landscape of Xuân Bay County, Ninh Thuan, Vietnam, the SANY 800-ton crawler cranes approach the Phase 3 site of the Jiangnan Wind Power Project. Their sheer size makes every movement a spectacle. The coastal winds, while ideal for energy generation, challenge even the most advanced lifting operations. The coordination required here is remarkable. Even small misalignments could spell hours of delay. Each crane will lift wind turbine components over 160 meters high, taller than a 53-story building. This feat was once impossible before breakthroughs in the design of the superboom developed in Huzhou, Zhejiang. The twin boom structure, welded in one piece, eliminates complex assembly steps and allows greater versatility without 90 degrees rotation. The robotic welding system continuously monitors preheating, alignment, and joint integrity, keeping tolerances within a millimeter, safety and precision in perfect harmony. High-strength steel pipes are assembled, machined, shot-blasted, and painted. Every weld undergoes 100% ultrasonic flaw detection 48 hours after completion, ensuring no cracks or defects. Components are then packaged with care, securing hydraulic and electrical parts from water and impact, ready for transportation to Vietnam. Trucks leave Huzhou factory for Shanghai port and then onward to Cam Ranh and Vinh Tan ports. Specialists inspect each part before final assembly. Once on site, the SANY 800T and 1 250T cranes lift towers and blades, contributing to a renewable energy future. Even the unexpected gusts of wind are handled, demonstrating the robustness of the design. Didn't expect the superboom to flex like that and still hold steady. The project transforms over 900 hectares into a windmill kingdom, producing 134 million kilowatt-hours annually, powering 61,000 households, and marking Ninh Thuan as a hub of clean energy in Vietnam.
Salzgitter Flachstahl GmbH produces steel that forms the foundation of modern engineering projects. Molten iron and other raw materials are processed in the blast furnace, where intense heat and chemical reactions produce liquid iron. Temperature probes ensure the furnace maintains uniform heat distribution across the charge. The flow is continuously adjusted to maintain uniform temperature and composition. Operators monitor the process, ensuring the molten metal meets strict quality criteria. The liquid iron is then directed to the steel mill, where alloying elements are added and the temperature finely controlled. Subtle adjustments in chemistry ensure the steel will have the required mechanical properties. Ladle stirring systems homogenize the alloy for uniform microstructure. The steel is poured into the ladle treatment plant, where further refinements remove impurities and homogenize the material. Slag skimming removes unwanted oxides, improving surface quality. Once treated, the molten steel moves to continuous casting lines. Here, it solidifies into slabs with uniform internal structure and precise dimensions. Automated sensors track temperature and flow rates, helping prevent defects. The slabs are inspected for surface and internal consistency before being transferred to the hot strip mill. Laser gauges monitor slab thickness to maintain tight tolerances. At the hot strip mill, slabs are reheated to optimal rolling temperatures and pass through successive rolling stands. The steel emerges as thin, uniform strips. These strips are cut to exact lengths in the cut-to-length line, ready for further processing. Cold rolling mills refine the thickness and surface finish of the strips, enhancing mechanical properties. Tensile and yield strength are periodically measured for quality assurance. Skin pass trains adjust surface texture for improved coating adhesion. Electro-zinc coating lines deposit protective layers, followed by hot dip galvanizing to provide corrosion resistance. Strip coating delivers the final finish, balancing durability and aesthetics. Steel production at Rail Mill Baotu by SMS Group in China follows a carefully orchestrated series of processes designed for high-quality rail manufacturing. The journey begins in the 330-ton LD-BOF converter, where molten iron is transformed into steel. Operators monitor temperature and chemical composition to ensure alloy consistency and eliminate impurities. The RH vacuum degassing process follows, rapidly reducing carbon content and further refining the steel. It's fascinating how quickly the chemical adjustments translate into structural improvements in the molten material. The aluminium heating furnace ensures uniform heat treatment before the steel is poured into the 2x2 strand slab caster. Fully pre-tested components and optimized startup curves allow slabs to solidify with consistent dimensions and internal structure. Butterfly ladle turrets lift and rotate independently, guiding the molten steel accurately. Engineers constantly adjust pouring parameters to maintain smooth, defect-free surfaces. Once cast, the slabs enter the hot strip mill. The walking beam reheating furnace brings them to the optimal rolling temperature. The first and second breakdown mills progressively reduce thickness with high roll forces, while hook-type tilters flip the billets precisely between passes. The CCS finishing stands, including universal and edging configurations, shape rails to exact geometries. Hydraulic adjustments and automatic gauge control maintain tight tolerances, even at rolling speeds up to 8 meters per second. The precision in every roll pass highlights the skill and technology involved. After rolling, rails pass through the cooling bed, cropping saws, and horizontal and vertical straightening machines. Each rail is inspected and stamped with a unique identifier for traceability. Only rails meeting stringent surface and internal quality standards proceed to the finishing line. It's impressive to see how each stage balances speed, quality, and safety. Discover how molten steel channels energy into every industrial component at ThyssenKrupp CSA, Brazil. The converter carbon steelmaking process handles iron and scrap steel, converting them into high-quality steel through precise oxygen blowing. Temperature and chemical composition are constantly monitored, ensuring the steel meets strict standards. After initial refining, the steel enters the ladle treatment stage, where alloying elements such as manganese, silicon, and vanadium are added. Thermocouples and advanced sensors measure temperature gradients, while stirring systems maintain uniformity. The subtle changes in chemical balance can significantly impact strength and ductility, which is fascinating. Continuous casting lines then solidify the molten steel into slabs, preserving dimensional accuracy and reducing internal stress. Cooling rates and slab thickness are tracked using laser gauges and flow meters. In the hot strip mill, slabs are reheated, rolled, and trimmed to customer specifications. Electro-zinc coating or hot dip galvanizing can be applied for corrosion resistance. Every step is logged and monitored through automated control systems. Steel moves steadily along the warm strip mill at Salzgitter Flachstahl GmbH, gradually transforming thick slabs into extended coils that can reach lengths of up to 1.5 kilometers. The controlled heating process ensures the metal reaches optimal rolling temperature, while sensors monitor thickness, flatness, and temperature to maintain uniformity. It's striking how small variations in speed or roll force influence the final mechanical properties of the strip. Slabs pass through multiple rolling stands where precise adjustments in roll gap and velocity shape them into thinner, consistent strips. The hot strip cut-to-length line then trims these strips to specific widths and lengths, tailored for various industrial applications. Observing these operations sparks an appreciation for how complex and coordinated the process is. Cooling beds allow the strips to gradually stabilize, minimizing internal stress. Skin pass trains subtly refine surface texture, enhancing coating adhesion and final appearance. Electro-zinc and hot-dip galvanizing lines provide protective layers, while strip coating adds the last finish. Each coil leaving the line carries the result of careful thermal management, mechanical control, and continuous monitoring. Even the smallest change in roll speed can ripple through the material, affecting quality. Seeing steel extend into such long coils is surprisingly captivating. Serve automotive, aerospace, and energy sectors. Inside the forge, billets are brought to glowing heat for shaping. Hydraulic presses deliver immense force, reducing their cross-section step by step. Each stroke refines the form, guiding steel toward required dimensions. The line continues with trimming and cooling, ensuring every forged piece leaves consistent and reliable quality. At Sarbach, extrusion reveals steel's transformation under controlled force. Heated billets are placed into the press, where hydraulic power drives them through shaped dies. Each pass defines consistent profiles. The process ends with cutting and cooling, producing bars and tubes prepared for demanding industrial applications with impressive reliability. The sight of steel forged into giant rings begins with a dramatic force, a 1,600-ton hydraulic press shaping the raw billet. Each strike flattens the heated block, creating the initial form required for ring rolling. The sheer weight of the press commands respect with every stroke. At this stage, forging temperatures often reach above 1,100 degrees Celsius, ensuring the steel remains ductile under load. Once the preform is established, the glowing piece is transferred to the ring rolling mill. The mandrel inside the hollow center pushes outward, while the main roll reduces thickness. It is remarkable to see how controlled power reshapes metal so fluidly. The diameter expands steadily as operators monitor the exact progression. Side rolls are engaged to maintain alignment, preventing distortion as the ring widens. Every adjustment reflects the skill of the team guiding the process. The balance between roll speed and hydraulic force ensures structural integrity. Hydraulic actuators synchronize pressure across rolls to maintain uniform wall thickness throughout expansion. As the cycle continues, the ring achieves its final dimension. The equipment demonstrates consistency while handling tons of material in motion. Cooling follows immediately, locking in the mechanical properties gained through deformation. Water sprays and controlled air cooling are combined to achieve the targeted hardness profile. Cutting operations remove excess material, leaving a clean geometry. It is fascinating to imagine these rings later supporting turbines or heavy machinery. The process concludes with inspection, confirming accuracy in size and roundness. Each completed ring stands as proof of both power and precision in metal forming. The process of seamless ring rolling begins with pre-forged discs, serving as the raw material. Heated blanks are brought onto computer-controlled rolling mills, where radial and axial rolls apply up to 250 tons of force. Each stroke compresses the volume, improving the internal structure. It feels powerful to see such force channeled into controlled forming. Advanced monitoring ensures diameter, height, and thickness stay within tight tolerances. Rings can reach 3,500 millimeters in diameter, 850 millimeters in height, and weigh up to 8 tons. The scale of production is impressive, showing both strength and accuracy. Final products become gears, bearings, seals, and components for heavy industries. Heat radiates across the hall, and each process pushes steel toward its next purpose. Molten metal flows into giant ladles, glowing intensely as cranes transport it to the next stage. The brightness almost overwhelms the eye, a reminder of the energy contained within. In the casting area, liquid steel is poured into molds, solidifying into long slabs. Continuous casting reduces waste and improves material consistency. It is remarkable how controlled systems guide such extreme conditions with reliability. These slabs then enter reheating furnaces, regaining the temperature needed for rolling. Powerful mills reduce thickness and extend length, shaping the slabs into flat products. The rhythm of rollers pressing hot steel is captivating. Finished coils are cooled, cut, and stored, ready for further applications worldwide. A single casting of 160 tons demands an impressive sequence. Molten iron flows into giant molds, solidifying into components that will later support heavy industry with strength. Bronze, cast iron, and aluminum come alive here through molding and casting. Induction furnaces melt the charge, molds are prepared in sand or wax, and each pour sets the shape. The results span heritage reproductions, rail parts, and artistic creations. Steel billets are heated to glowing temperatures, becoming pliable for shaping. Each billet is carefully positioned under the hydraulic press, where immense force reshapes it into the desired form. Hydraulic and mechanical presses deliver immense force, forming each part. Workers monitor alignment and dimensions carefully. Final inspection confirms quality, durability, and conformance. It's impressive to see raw metal transform into precise, functional parts under controlled force. Steel shaping takes center stage in this workshop, where pneumatic forging hammers drive the transformation of raw metal into robust rings. The sound of each strike resonates with energy as billets are heated to optimal forging temperatures. Each hammer delivers controlled force, compressing and elongating the steel with remarkable consistency. The glowing metal reflects the intense heat and the potential contained within each piece. Operators constantly monitor alignment and press settings to ensure uniformity. After initial forging, each heated billet is placed carefully on the press bed. A hydraulic press descends with tremendous force, piercing a hole through the center of the billet. Once the first billet is formed, the operator positions the next billet, which is pressed through the same opening to continue shaping the ring structure. The cycle repeats, producing rings with exact diameters and wall thicknesses. The finished rings carry the strength and accuracy required for demanding applications in flanges, bearings, gears, wheels, and sleeves. Finally, the components are ready for shipment, demonstrating the interplay of mechanical power, thermal treatment, and skilled craftsmanship. Bright steel rods line the floor, ready to transform into perfectly rounded 120mm balls. Heated billets are fed into the skew rolling mill, where synchronized rollers shape each sphere. The machine exerts intense pressure, forming precise dimensions. Operators monitor temperature and alignment, ensuring uniformity. Post-rolling, balls are cooled and inspected for roundness and surface quality, ready to serve demanding industries like mining, metallurgy, and cement. The process highlights both mechanical force and technical oversight. Metal rods are cut to size before being heated to optimal forging temperatures. Skew rolling mills shape each rod into 120mm steel balls, with continuous monitoring ensuring uniform hardness. Operators inspect every ball for surface defects and dimensional consistency. Final quality checks confirm the balls meet strict industrial standards. The process demonstrates how controlled heat, rolling force, and human oversight combine to produce durable grinding media. Raw steel is pushed through presses, emerging as sturdy, precision-forged components ready for industry. Skilled operators place each billet under 1 or 2 column hammers, delivering tremendous impact to shape preliminary forms. It's fascinating to observe how each strike redistributes metal internally, creating strength and structural integrity. Complex forgings weighing up to 70 kilograms are produced with repeated hammering and trimming. Hydraulic presses pierce, calibrate, and refine critical parts like hooks and connecting rods. Machining centers, both NC and CNC, create precise profiles, while electric discharge machining enables deep and intricate shapes. Heat treatment lines perform normalizing, softening, and isothermal tempering to enhance durability. Blasting and coating processes prepare surfaces for corrosion resistance and assembly. Every step is accompanied by rigorous mechanical and metallographic testing to ensure material performance. Finished components undergo final inspection, verification of dimensions, surface quality, and packaging for safe shipment. Operators continuously monitor machinery and processes, guaranteeing consistency across thousands of units. The combination of human skill, advanced technology, and systematic quality control secures reliable components for railways, construction, energy, and heavy industry. Every turbine shaft must endure extreme forces while maintaining flawless performance. At Schmiedewerke Granite, these components start as massive steel blocks designed for demanding energy applications. Alloying adjustments and temperature fine-tuning ensure chemical composition meets strict specifications. The largest ingots weigh up to 76 tons. It's striking to see such immense mass guided and controlled with expertise. Pre-forging heating raises the blocks to 1,200 degrees Celsius, preparing them for the meganewton press. Billets are positioned and forging begins, upsetting critical areas for optimal ratios. Turbine shafts and wheels undergo successive forging passes, guided by computer-controlled tools. Heat treatment follows, with vertical quenching in oil or water for shafts up to 8.5 meters long. After that, components enter machining stations where lathes and milling machines refine geometry, ensuring precise tolerances and surface finish required for high-performance turbines. Then ultrasonic inspections, tensile and impact tests confirm quality and integrity. After marking and final inspection, components are dispatched, ready to perform under extreme operational demands. Steel from Saarstahl carries the force of mobility and energy in every beam and sheet. Slabs are cast and rolled, maintaining strict temperature and surface standards. Heat treatment enhances durability and flexibility. The rhythm of machines and human oversight creates a tangible sense of strength. Final inspections confirm that each bar and sheet can withstand demanding applications, ready for global delivery. Molten steel glows as it is poured from overhead ladles into molds designed for precise dimensions. The temperature of the alloy is continuously monitored to maintain optimal flow characteristics. Workers guide the ladles along their tracks, adjusting gates and risers to ensure complete filling. The molds are preheated to reduce thermal shock and ensure smooth metal flow. Operators check alignment to prevent uneven casting surfaces. After pouring, the metal is allowed to settle to release trapped gases. Workers inspect the surface for minor imperfections before cooling completes. Air circulation systems help stabilize temperature around the molds. Temporary supports hold the molds in place while the metal hardens. Watching the liquid transform into solid shapes highlights the raw energy contained in steel. After initial cooling, molds are removed, and the cast pieces undergo fettling to remove excess material and smooth surfaces. Finished components are sorted and prepared for shipment, with each piece documented for traceability. Arrangements of molds set the stage for controlled metal flow in sand and investment casting. Molten alloys are monitored for temperature and composition before pouring into molds. Cooling and solidification are controlled to prevent defects. Once set, castings are removed, cleaned, and machined. Components undergo ASTM standard tests, including tensile and impact measurements. Engineers document each step, ensuring consistent quality. The final pump and valve castings reflect decades of expertise. After initial shaping, components move through quenching tanks, solidifying their strength. Forged round bars enter the hot rolling plant, where high-capacity presses shape rings and other parts. Band saws and lathes refine dimensions, while oxygen cutting and milling complete the preparation. The combination of heat, force, and skilled oversight ensures reliable, industrial-grade components. It's striking to see the scale and coordination required for each piece. Wax forms are prepared with precision, serving as templates for complex metal parts. Rapid prototypes are now produced with 3D printing technology, allowing complex geometries to be tested and refined. Wax patterns are assembled onto wax trees, connecting multiple pieces via gates to guide the subsequent metal flow. Next, the ceramic shell is applied in repeated layers using automated dipping and stucco application, forming a heat-resistant mold. Once the shell is dry, wax is removed through controlled burnout in high-temperature furnaces. Metals, both ferrous and non-ferrous, are melted using induction or electric resistance methods, reaching precise temperatures before being poured into the preheated molds. After solidification, the ceramic shell is removed with mechanical or high-pressure water methods. Sprues and gates are cut and ground, leaving individual castings. Components undergo finishing treatments, including vibratory media, belting, or hand polishing, achieving smooth surfaces and tight tolerances. Machining is performed on CNC centers when necessary, handling challenging alloys like 17-4 pH stainless steel or cobalt nickel. Each casting is inspected, tested for mechanical and chemical properties, and certified, ensuring readiness for aerospace, defense, automotive, and energy applications worldwide. The precision and control at every step reflect the dedication and expertise of the foundry team.